Okay, what we're moving on to now is the derivative. And it's important to understand the context of the derivative and where it comes from and why you would be motivated to look for the derivative. In general, the function rule, right, I tell you the domain, that's an x value, and you have to assign a y value, the value of the function to that. It's complicated. I mean, we saw in the first lecture the implicitly defined function, for example, the logarithm and so forth. So again, it's complicated, right? I mean, it could be implicitly defined, as in the first lecture. It can be implicitly defined in the form of a differential equation, conservation of mass, momentum, and energy. It's not often possible to explicitly write out the function. So again, it's a complicated situation. So what do? You just throw your hands up? You have to do something. So what we're going to do is give up on the idea of getting the function rule globally. In other words, over the entire domain of the problem. And focus our attention locally, right, in the neighborhood of a point. I'll make these concepts a little more concrete as we go. Okay? So we're going to focus our attention around the point. Let's see how that works. Here's just a typical example. Let's just take f of x equals x squared, just again for something simple. As I said, in general, you won't know the function, and these ideas are going to build up into the fundamental theorem of calculus, in fact. So, okay, here's an example of a function. Now, again, let's pretend we don't actually know all this. I'm going to give up trying to figure it out globally on the entire domain, on the entire real numbers. Let's just focus our attention in a neighborhood of this point here. 1, 1. Okay, so let's just focus our attention. Let's just say a line, because it's the easiest, non-trivial. Like a constant is maybe a little too easy. So let's move up on the food chain and consider a line. Okay, and then later on we'll see you can do more than that. Any polynomial. A polynomial of various degrees. But anyhow, for the moment, let's just focus on a line. Well, what do you need for a line? Again, notice that the argument here, right? I'm going to give up on global and I'll focus local, right? Just try to get an approximation right around here. Okay, that's what local means. What kind of an approximation then? Again, notice how you're reasoning your way through this. A line, I mean, the easiest possible function that isn't a constant, I guess, would be the easiest, but a line, right? So a line. And if I'm going to do a line, how do I do a line? I need a point and a slope, right? That's what I need for a line. So this is what's so clever about this. It's, again, what I want you to understand is the reasoning argument here. This is what's really important, and then what we're doing. So I need a point and a slope, right? So how do we even get this? All right, what point and how do we calculate a slope? Well, let's start. We have to start somewhere. The point here will represent the state of the system today, right? So assume we're talking about time. So the time would be today, and this value, the y value, would be the state of the system today, right? The state of the system today. So that's our point. We want to focus our attention. So I'm not going to try to predict the weather through all time. I know the weather today. I'm trying to predict the weather tomorrow. That's what I'm going to live with. That's what I hope to do. Now, if we want a line to predict this, I mean, just draw one on the picture. You just draw one. That's the ideal scenario. Okay, you know it's a tangent line, whatever. Let's just say you draw it on the picture. That's our line. You can see locally it's pretty good here, right? If you just keep your attention focused in this little neighborhood here, right? In other words, I'm not going to try to approximate it down here or way over here or further out. I'm just going to narrow my attention to a little to the left of one, a little to the right of one, and we'll talk about that more later. But I mean, you can see it's not too bad right here. Okay, the question is, I have the point, right? I have the point. Now, how do I calculate the slope? Well, do it. I mean, give me an answer. Give me an answer. How am I going to calculate a slope? So pause the video and think about this. Again, it's a great challenge for you. How are you going to do it? I want the most basic, simple engineering approach you can give me to solving this. Again, people were trying to solve problems with calculus. They weren't just sitting here trying to develop concept for concept's sake. Give me a slope. I need an answer to this problem if I'm going to move forward, okay? Okay, let me jump in then if you thought about it. Just pick a second point. Just pick a second point. Then you have rise over run. And you say, well, okay, that's kind of arbitrary. All I'm telling you is this is the most classic engineering solution. I need a slope. Okay? Now you say, well, the secant line is a line that connects 2 points. Right? It's not perfect. I mean, again, the tangent line, the blue line, is your best case scenario, but it's workable. It's workable. So I'm going to connect x is 1 and y is 1 to an x is 2 and y is 4. So I can rise over run, I can calculate a slope. And there's nothing wrong with that, right? I mean, there's absolutely nothing wrong with this, right? So I can calculate my second point, and from that I can calculate the slope, rise over run. And then I can calculate the equation of that secant line, right? So notice, 1, 1 is fixed. If I pick x equals 2, notice everything is set in motion. I have the y value because it's a function. Again, don't ignore that. I know there's a y value because it's a function, and I'm told how to calculate that. I'm told the y value is 4. So when I pick x is 2, I get not only that slope, right? When x is 2, I not only get that slope, I get the equation of, I can calculate the equation of that secant line, right? So the number 2 gets associated with both the slope and the secant line. Okay. Now you're in the group meeting and you say, that's a great idea, but I can do you one better, right? I mean, I'm bucking to steal your thunder here. So instead of going all the way over to 2, I can get a better approximation if I only go to 1.5. So in your face, smarty pants, right in your face. I'm only going to go to 1.5, and so look at the picture. The second secant line is a little better than the first one in terms of what I'm looking for, right? In terms of what I'm looking for. So I can follow the same procedure. If I pick x is 1.5 or 3/2, I can calculate the value of the function. I can calculate the slope of the secant line, rise over run, right? So I can get the equation of the secant line there. So again, when I pick x is 2, I get the point, I get the y value, I get the slope, right? Oh, when x is 1.5, right? I get the y value, I get the slope, and I get the tangent line. I get 3 things for free, right? I mean, this is what I get. And again, you can continue to one-up yourself. Everyone in the meeting's got to throw in their 2 cents at this point. But okay, we get the jokes now, right? So I can go to 1.25. That gives me a y value. That gives me a slope. That gives me my secant line. So again, when I say x is 1.25, a number of things come to mind, 3 that I've just listed. And you can look at the picture physically. This is doing what you want it to do, right? If the blue case, the tangent line, is the ideal scenario, then each of these secant lines is a better approximation. The result is getting better and better as I take values that get closer and closer to 1. Now at this point you should be thinking of something that we've already done, right? Not from nuclear physics, not from your psychology class, something we've done. What springs to mind here when I talk about that? I'm getting a better and better answer as my x values get close to 1. I'm talking about a limit. I think this is where actually the limit idea was coming from, right? You're trying to approximate the solution to basically the conservation momentum equation, fundamental theorem of calculus. Okay, so let's go on with this. So I can see that I'm getting some kind of convergence, okay? But I can't really describe that. I mean, okay, I can see it from the picture, but how do I actually make that mathematical? I mean, to your eye, that may be converging, and I might just want to play the troll and say, no, it's not, right? So how do you actually come up with a definition? What is converging, right? So again, it does look like we're on the right idea. Our engineering approach is correct, but how can you make this precise? Right? How can you make this precise? We have the tool of the limit. Clearly, there's some kind of a limit in here, right? The x values are approaching 1 from above or below. It's the same. You get the same thing. Okay, so how do I make this precise? Well, again, use your think. What's happening here? Well, I need a point and a slope, right? I need a point and a slope if I'm going to describe a line, any line, tangent line, any of these lines. So for all these secant lines, notice what's in common. They all exactly have this same point in common. So clearly that's not it. They all have the same point in common. So a line is defined in terms of a point, which is the same for all of them, so that's not it, and a slope. If you look at these pictures, what do you notice about the slope? The slopes are getting close to the slope I1 for the tangent line, right? The tangent line also has the same point. So notice, as x values get closer and closer to 1, these slopes of these lines are approaching what I want to be the slope of the tangent line, right? I mean, that's pretty clever. Again, the issue is, in any kind of engineering or science or math, whatever, you only have a limited number of tools. This is one of the things I'm trying to get you to see. So far, all we have is 2 ways to evaluate the limit, right? Plug in directly or evaluation theory, sign intermediate value property. That's it. That's all we have. So we have the limit and the sign intermediate value property. This isn't sign intermediate value property. And as I said, calculus, what makes calculus calculus is everything is based on the limit. Okay, so here's a good case. Look at the power of what we're doing. We're basically coming up with a way to show that these secant lines approach this tangent line. So again, y equals mx plus b. Okay, I don't have it in the 2-point formula, but I don't really care. The point is fixed. So the only thing that's flexible here is the slope. Right? All points go through there. So I make a table. For my first secant line, my point was 2. My slope was 3. For 1.5, when x was 1.5, right? For my second secant line, my slope was 2.5. For the third point, notice all these x values keep getting closer and closer to 1. Yes, from above, but it would work exactly the same from below. And notice what's happening to the values of my slope. Notice this is exactly the kind of calculations we did in the second lecture when we talked about limits. Exactly, we just made a table. And my guess for the slope of the tangent line is 2. Now it's a guess. We need to make it more precise. So this is the idea. We have to make this mathematically formulated. We have to mathematically formulate this concept. Now these are just numbers. So what's my function? Remember, you can't take a limit without a function. I'm sorry, you can't. You need a function. So what is the function? Right? It's going to be a slope, right? Rise over run somehow. And it's going to connect the point out here with 1, 1. Right? So let's just talk about this for a little bit, right? For the tangent line then, let's just say we calculate it. We'll come back to calculating it precisely in a moment. We have a point and a slope, and look at my picture. That's my equation of the tangent line. Now we calculated the slope just by, we made the table. That's probably one of the least precise ways of figuring it out. But again, fine for the moment. For the moment, we'll make it more precise. So my point's 1, 1, my slope is 2. You plug it in, you get this equation of the tangent line. Now let's see how this works. First of all, it's an equation. So what I want to do is I want to approximate our function f by another function. So okay, instead of calling it an equation, I'm going to turn it into a function, and that function is called the linear approximation. I think the name speaks for itself, right? It's a line, and it's an approximation of the function. Once again, the terminology isn't there to intimidate you or to mislead you or to make your life painful. I'm going to ultimately replace the function by its linear approximation. And we'll talk about why that works and how you look at that. But you can see around this point, 1, 1, it's pretty good. Now I plotted, I'm just plotting values here, just to make my point. These are the values, so for the x values between 0 and 2, I plotted the value of the function, and I plotted the values for the linear approximation. And okay, they both go through 1, 1, right? When x is 1, y is 1. And you can see it's not too bad. For example, at 0.9, there's an error of 0.01, right? And you can see the error gets bad as you go away, right? The distance gets worse. At 1.1, the error is again 0.01. I mean, it's not too shabby. At 1.2, the error is 0.04, right? So again, it all depends. If you want a more accurate approximation, just stay closer to home. Stay closer to 1, 1. You can already see how the term neighborhood comes in, right? So if you want a more accurate approximation, stay closer to home. It makes sense. So the ultimate idea is to replace the function, which I don't know, with the linear approximation that's easy to find. Fundamental theorem of calculus. Hold on to that. We'll come back to this a lot. Okay? So this is the idea. And I'm just plotting the error right here. So here's the distance from home. Here's the distance from home. And again, you can see if I go further away from home, right, the error gets worse. If I stay very, very close to home, the error is pretty good. And again, these are the kinds of calculations you look at in reality. What's the error? Test cases where I actually know the solution and I do my linear approximation or my approximations so I can test my approximation scheme. And so this is what we're talking about in a neighborhood. You're really limiting an XY patch, right, in such a way that you're going to replace the function by its linear approximation. If you want a more accurate approximation, take a smaller neighborhood. Now, a neighborhood is really an XY box. So if I want it more accurate, take a smaller neighborhood. Okay? Since we're talking about limits, we know that the slopes of these secant lines is in fact going to converge. And that gives us the slope of the tangent line, right? So, okay, so again, just reading comment. So for example, if I want an accuracy of 0.2, actually I think it's 0.02, I think that might be a typo, I could go back and check. But I limit my neighborhood to the one I drew in the box here. I mean, so it's relatively good in this box. I mean, again, if you want it more accurate, okay, I do have some error here and here. I just take a smaller neighborhood. Instead of going from 0.6 to 1.4, I just go from, something much smaller, 0.9 to 1.1, for example. It could be 0.2. Okay, it looks like there's some error here. But I take a smaller neighborhood. And that's a main idea of calculus. This is actually calculus. Not taking derivative of x squared is 2x. That whatever. The calculus is this. This is how we actually use calculus when we're solving problems. Okay? Again, the idea of replacing the function by its linear approximation locally is one of the main applications of calculus. This is the concept behind the fundamental theorem of calculus. The real fundamental theorem of calculus, not the kind of whatever. We'll get there. We'll get there. We'll get there. You'll see. Now we want to make this all precise, and don't look at me with those eyes. Just don't look at me. Don't look at me with those eyes. We need to make it more precise, right? So we need to firm up this idea of limit. So let's go back to that. This is what we had originally, right? I had the first secant line, and again, all of them were based around 1, 1. So I picked a second point was 2, and I got a slope of 3. The second secant line, I got closer. I picked 1.5, and the slope was 2.5, and so forth. Right? So we can see that there's some connection here. But to do a limit, I need a function. Again, you have to understand, you cannot do a limit without a function. You need a function. The function is clearly going to involve the slope. Again, follow my reasoning. You see where this is all coming from and going? So I need a formula for the slope. And how about that one? Slope is change in y right? Change in y over change in x. That's the slope function. And if I write it in this form, you tell me an x value, say 2, plug it in here, and you'll get the value we got before. So let's just follow this through and see how this is going to work. So this is as a function. Again, you can plug in 2 here, 3/2, 1 1/4. You'll get exactly the same numbers we got before, only this is function form. And that's good because we need to do the limit. So for x squared as a test case, just plug it in. Look what happens. Now, of course, this function is never going to be defined when x is 1. So clearly, if we have a function and we're looking at a limit, we're not going to be able to use the plug-in version of it. We're going to have to think about the extension theorem, right? I'm just thinking ahead. Now, of course, these cancel. Right? It doesn't cancel, it equals 1, right? X minus 1 over x minus 1 is 1. And so this is it. Now, this is still not defined as at x minus 1. At 1, I mean, you can say the rule is, but this is a function. We'll make it a lot more here, more precise. This function is not defined at x equals 1. It's not. A over b is 0. So again, if I wanted it defined there, I couldn't have this term in the denominator, right? That's how it works. But the rule, as long as I'm not at 1, is x plus 1. And that's the picture. Notice it's not defined at 1. Right? So I have a function. Again, notice how I develop all the ideas. I don't start in the most difficult case. I pick one of the easiest possible test cases and I build out from there. It's always easy to start solving problems. Just draw a picture. This is when they say you're brainstorming on the back of an envelope or something like that, or on a napkin. This is the kind of thing we're talking about. Okay? So I have my function, my slope function. Right? This is the slope of the secant lines. And I'm going to look at its limit. And remember, the limit is a number, and I'm going to call it m for slope, in fact, or m tangent, slope of the tangent line is what we're going to take it to be. And I have to plug this in here. I need an extension. In this case. So again, notice I keep the rule to be exactly the same, right? But I extend the application of that rule so it can include 1. And then the extension is a polynomial, right? So I can just plug in, and then I just evaluate it as 2. So we got what we, that should be an n. I don't know if it's an n, that's a typo. We did it the same way. It was just about, again, the physical situation, transforming it into a way that we could apply our mathematical tools. And the only tool we had was the limit. Notice everything in calculus we've done is based on the limit. That's what calculus is. Okay, so again, we're transforming the problem. We have to define a function if we're going to do limits. That function is going to be the slope of the secant lines. So we obtained the slope of 2 not just by looking at a table of numbers and guessing, by actually doing setting it up in a mathematical framework and evaluating it using mathematical tools, the extension theorem. Okay, so I mean that's pretty powerful stuff. Again, this is the interest. This is what calculus is. It isn't the pain of the algebra. It isn't pages upon pages of mind-numbing calculations. This is calculus. So let's make it precise in the general case. A function is said to be differentiable at a point, provided this limit exists. Provided this limit, it's a number. So I don't have 1 from the left, 1 from the right, for example. For example, it doesn't go to infinity. It's not an infinite limit. It has to equal a number, this limit. And again, from the left and from the right. And of what? What's m? M is the secant slope function. It's the slope of the secant lines. Right? That's how we calculated this. So this is what we have. Clearly, this function cannot be defined at A. Right? It can. So you know the tool you're going to use always here is the extension theorem. There you have it. I mean, it's so nice. This is calculus. This is the brilliance of thinking. Now we're just going to do a lot of examples as technicians. But I mean, this is what's actually interesting, and this helps you understand how it works, where the fundamental theorem comes from, of calculus comes from, and how we actually use it to solve problems. That's the key. I'm interested in solving problems, and no, not by taking derivatives. Okay. And I'm just emphasizing again, you have to have the limit from the left, you have to have the limit from the right, and it has to equal a number. We're not talking about infinite limits here. You have to equal a number to have a slope. Okay? So, again, I'm emphasizing it's a number. Why? Because you see problems like this, and people have a function here. It's a number, and I'm calling it the slope of the tangent line. So the tangent line, I see what I'm doing. The tangent line, definition, the tangent line goes through the point we specified. Remember the previous example, right? For a line, I need a point and a slope. By definition, it goes through the point and has this slope. That's what I was saying. It goes through that point and has that slope by definition. Again, that's what a tangent line is. It has this point and this slope derived from the limit of the slope of the secant lines. Okay, that's pretty good. Now we're going to set about just calculating a number of things. I wrote it all out here, but I wouldn't memorize this formula. We'll do a lot of these problems. It's just too easy to calculate. Y equals mx plus b. That's the slope. That's the point. You'll see. And then I can also write, okay. What I wanted to emphasize next was the notation. Okay, people get really hung up on this stuff. But once again, terminology and notation should be there to help you. Now, I don't really want to call it slope of the tangent line. I could. I mean, there's no problem with it. But I want a notation that emphasizes where it comes from. Why pick the notation dy dx and x equals a? Because, again, notice it's a function. If I tell you that x is 1, it's a function. By the fact that it's a function means there's an xy value there. So I'm really saying at a point. So this is really saying a slope at a point. Why pick dy dx? Why? Well, notice what you do. What do you have here? How did you calculate this if you have 2 points on a graph? Change in y over change in x, right? I mean, that's what a slope is. Change in y, change in x, right? Delta y, delta x. Well, notice, delta is the Greek d. So I can't keep calling it delta, right? I mean, it's already been taken. So call it d. dy is dx. This notation is to remind you change in y over change in x of the tangent line, not the secant line, of the tangent line. Change in y, change in x at this point. Okay, if I specify the x value, it's a function, so there is a y value, there is a point. All that's contained right here in this notation. It's not random. Again, don't be confused. It's not random. It's not my particular notation. It's in the book. Google it, whatever you want to do. It's a standard notation. And that notation is to remind you that it's a change in y over change in x, not the secants, right? Not the secants of the tangent line, right? D, Greek delta, English d, dy dx, or I guess it's Latin, at x equals a, and again, it's a function, so there's an xy pair. So that's where it comes from. And really what I want is a function. See, the tangent line is an equation. The linear approximation, which is the function version of the tangent line, just replace the y with L. L stands for linear. I mean, what do you think? We'll do a number of these in the problem section. So, I mean, we'll look at this in detail. All right, so again, the relationship is y equals L of x. Okay, so let's look at an example. Let's just look at the example we did before. F of x equals x squared. Okay, f of x equals x squared. And I want to find, again, the slope of the tangent line when x equals 1. So 1 will have a y value at that point, right? Change in y, change in x, but at the tangent, right? dy dx. So that's what it says. So let's again start a formal, let's do the process. And again, my notes on working out the problems are like the version 2, it'll be better. But I want to check that the function is in fact defined there. If the function is defined there, is not defined there, I can't have a tangent line. There's no point, right? So you have to first check the easiest things first, write your error protocol. Make sure the function is defined there. And you can say, well, that's stupid. Come on, whatever you want to do. But if it's not defined there, the problem's over. Error protocol, leave the code. Okay. Next thing I want to do is calculate the secant slope function. Right? And this is its definition. Right? So notice this function is derived from f. So I have f of x minus f of 1, x minus 1. Notice it's not defined at 1. And you just substitute in, right? What's the function? X squared. You have to simplify. We need an extension, right? We need an extension. So x plus 1. And again, notice the domain of this function is here. Okay, so here's my function. And I want to evaluate its limit. By definition, remember, by definition, the slope of the tangent line, that's what this is, dy dx, at this point, is the limit of this function. Now it's no longer it's a concrete limit problem. Just do it the same way you would always do a limit problem. Forget where m comes from. I need an extension, right? I need an extension. And the extension is a polynomial, so it's continuous. And I just evaluate it. What's n of 1? 2. So by definition, the slope of the tangent line is 2. And that's exactly what we got before. Only this is all set up in the mathematical context. And you can generalize this to anything. So again, find the tangent line. These are the standard questions that I'm going to ask you on tests and stuff. So now that you have a slope, find the tangent line. Right? The tangent line is a point and a slope. Notice I have a point. If you tell me x is 1, then I can tell you y. Y is f of 1. So I have the point 1, 1. Right? From the previous example, I have the slope. So just plug in. Here's the equation of the tangent line. Again, I don't like memorizing formulas. I mean, you knock yourself out. A line looks like y equals mx plus b. And you can say there's a point slope of a version of a line. Do you save any work if you use that? I mean, look what I'm going to do. You're not doing it any quicker. I don't know why you need to know that. I'm just going to plug in the slope. Just plug in the slope, too. Plug in my data. That's my point, right? My point is 1, 1. Plug the 1 in for x and plug the y value in, I don't know, for y. And solve. I mean, it's that easy. We're going to do this a lot, and it's always going to be that easy. So that's the equation. And then what I want to do is I want to turn it into a function, right? A function. So how am I going to proceed here? Easy. If that's my tangent line, that's my linear approximation. And again, I'll be more precise about this in later examples. This was an earlier version of the notes. Okay, so that's my linear approximation. Here's another example. Why don't you try this? I mean, it's going to work the same way. The difference here, and this is why you're not going to like it, there's algebra. There's an algebra issue here. Not calculus, but algebra. Okay, so hopefully you tried it and you'll see what I mean. Let's go through it. Let's go through this. I checked the point. Is it defined? Yes, yes it is. Right, it's defined. That's great. I'm going to calculate the secant slope function. And this is why you don't like math. And I get it. I really do. I mean, I'm not going to say you don't like math, okay? But I get it. I get why it can be painful. This is a difference of cubes, right? This is a difference, and it has a formula. It factors, right? You can either use polynomial division or memorize the formula. And again, it's a purely algebraic step. But again, unless you're very confident or know these things, yeah, I mean, you feel put upon. I mean, I get it. I'm not going to make you memorize formulas for the test. I'm not going to try to trick you. I mean, I want you, if you put some effort in, I want you to get something out of this class. And I don't want to make it a hazing experience. Now, you may not feel that way, and I hope you don't. But, again, I like the ideas here. I think it's really clever stuff. But this is just an algebra step. So this is the rule that's equivalent to that rule. Notice again, the function is not defined at 2, the secant slope function. Right? The function is, right? The function is defined at 2, but the secant slope function clearly is not defined at 2. Here's the picture. Here's the picture. I just graphed this. I just graphed this, but it's not defined at 2. Okay, so you can see it's going to have a limit, right? There's a limit from the above and below. It's going to be 12, I'm guessing. Here's the calculation. I define an extension, right? I define the extension, and then I evaluate the limit using the extension theorem. All very standard stuff. And we're going to do it over and over again. So once I have the slope of the tangent line, the question is, what's the equation of the tangent line? And then what's the linear approximation? Pause and see if you can do it. Okay, here it is. Here's the question. I have a slope of 12. Again, I want you to see that this is so standard. Y equals mx plus b. That's the equation of a line, right? Plug in the slope of the tangent line is 12. Plug in your data, solve for b, and there it is. I mean, this is pretty basic. Okay? And then linear approximation, well, if that's the equation of the tangent line, that's your linear approximation as a function. Right? Notice, like, if you write a class structure, you have an output. That's a functional form, right? You don't have an equation form of that. You literally have a function, right? You have an output. That's the key. And here's the picture. Okay, again, we're going to do them all this way. Here's the picture. Notice around 2, when x is 2, that the linear approximation is pretty good. I mean, if you go between, say, 2.1, 1.9, and 2.1, it's good. Again, the smaller the neighborhood, the more accurate this is, right? A neighborhood is local. It's in the neighborhood of your house. Your home is at 2 here. That's where the terminology comes from. This is a piecewise function, right? This is a piecewise function. So I'm going to ask you to calculate the slope of the secant line at 1. So the function has one definition down here and another rule up here. So how do you calculate the slope of the tangent line? You do it exactly the same way we did it. But this is the kind of, okay, let's just do this. Let's do it correctly, I guess, first. Right, so I do have a value at 1. The function is defined at 1. That's my home. Right, I have 2 rules. So remember, so if I'm going to do the limit, right, if the function is in 2 pieces, the slope of the secant line, slope of the secant function is going to be given in 2 pieces, right? Because it's f of x minus f of 1 over x minus 1. When x is less than 1, right, this is the definition, f of x equals 2x. So I plug that in. This is only valid when x is less than 1. Clearly it's not going to be valid at 1, but the rule is x less than 1. If x is greater than 1, and not greater than equal, greater than, right, because it's not defined at 1, I plug in this rule and do the algebra and I get this. So the secant slope function is piecewise. But that's not a surprise. If the function is piecewise, the slope of the secant lines is going to change depending on which side we're on and which rule we're using, right? So that's the issue. I mean, all we're doing is correct. And you can see the limit is going to be from the left and the right, which would make sense because if the function is piecewise, you do the limit of anything there from the left and right. Right? And again, it's not defined in 1. Here's the picture. Here's the slope of the secant slope function. It's 1, this constant, less than 1, and it's this function to the right of 1. Again, it's not a surprise, just piecewise. No surprise here at all. It shouldn't be if you thought about it. So let's go on. We just have to evaluate the limit, and then we're going to do it from the left extension, right? From the left, and we're going to do it from the right. Right? We're going to do it from the right. Have a different extension. But notice the left limit and the right limit are both 2. Right? Which means that the limit of the secant slope function is 2. Okay, so it exists. Now, if the limits were different, right, you would not have a limit and you would not have the slope of the tangent line. And that's it. So we have the slope of this tangent line at x equals 2. And again, how did we do it? We just followed the procedure. We didn't just do whatever we wanted. We followed the definition. Okay? So if you have the slope of the tangent line in a point, you can come up with a tangent line itself, the equation of a tangent line. Just plug everything in, plug in the slope, y equals mx plus b, plug in your data, solve for b, and you're done. It's very easy. And then you can do the linear approximation. And again, we can look at the picture. Look at the picture. You notice the linear approximation is exactly the same as the function less than 1 because the function is linear, right? So the linear approximation is exactly the same down there. And as you grow, as x gets larger, you see the divergence gets greater here. And again, in the neighborhood of 1, it's a pretty good approximation, and it does exist. I mean, that's pretty good. Now, this is toxic. This is just bad. This is what people do without thinking. And I know calculus, and oh, look, I got the answer. I have no idea what I'm doing, but I got lucky. So you're just ticking away. If you don't have calculus before, probably it's better. This is where a little knowledge is dangerous. I'm just ticking everything away. Oh, look, it's 2x. The derivative, tick, is 2. X squared plus 1, the derivative is 2x. I'm clever. I'm just going to look at the limit of each of these. And there, too, I got the right answer. And, well, 2 is the answer, but you have no idea what you're doing. I mean, if you were applying to a job for me and I did like an interview, Google interview with you, boy, you'd be out the door so fast for saying something like this. What did you just show here? You didn't show that the slope of the tangent line was 2, right? All you showed, here's the definition. All you showed was that the limit of the derivative, it should be at 1 here, right? A down here. All you showed is that the limit is x goes to 1 from the left and the right of the derivative is 2. I mean, that's all you showed. It's a coincidence, purely a coincidence, that 2 is the slope of the tangent line 2. It's purely a coincidence. But bingo, it's the right number. I got the answer correct, didn't I? I have no idea what I'm doing, but, you know, I stood on my left foot, faced east, chanted to my God, and I was rewarded. Job well done. And then we wonder why things don't go so well on the exam. All you showed in this case was that the limit from the left, the limit from the right of f prime as a function is 2. I mean, that's all you did. That's not the slope of the tangent line. That's the limit of f prime, which is not. Okay, so you have to be careful about these things, right? The slope of the tangent line is computed in a specific way. I'd have to look at the slope of the secant slope functions, not at this function f prime. They're different things. Okay. So again, I just want you to be aware of this. People make mistakes because they don't know what they're doing. Just follow the examples and know what you're doing. Now, if a function is differentiable, then the function is continuous. It doesn't work the other way around. Differentiability is smoother than continuity, right? It's a regularity result. It's a smoothness result. Here's your picture. Here's an example again of one-sided limits existing. The one-sided limits exist. We have a jump, but the limit doesn't exist. Here we have the limit from the left, limit from the right are equal, right? There are no jumps, but you see there's a hole here. So this is smoother than this result. Here, we filled in the hole, so we're continuous, right? The limit equals the value of the function. That's how we evaluate limits. And this is more smoother, more regular. And differentiability irons out that rough edge. Now, again, if you were going to look at the air temperature, pressure, density distribution in the room where you are, it's not going to have any rough edges like that. It's going to be smooth like this. So let me again point this out. Differentiability or smoothness or regularity is a mathematical description necessary in the model of the physical circumstance, right? It's necessary. So you look at conservation, mass, momentum, and energy, but you also have to say how smooth that solution is. And the air in the room is actually differentiable. It's actually smoother than that, but it's actually differentiable. So you can't have this kind of behavior, let alone this or this, relative to the air temperature, pressure, density in the room. So these are, again, important modeling characteristics. And here's an example. Here's the absolute value function. Find the slope of its tangent line and see what happens. Look at the picture, though. See if you can anticipate what happens. So everything's fixed around this point, right? What are all the slope of the secant lines on this side? Again, look at things. Think. So again, let's look at this physically and see if we can understand the answer. Okay, what we're doing is pick x equals 1, 1/2, 1/4. Again, think about the table. What are the slope of the secant lines? The way we did it originally. Change in y, we're changing x. Change in y is 1, change in x is 1, 1 over 1 is 1. Go to a half. Change in y is a half, change in x is a half, 1/2 over 1/2, it's 1. Go to a quarter. 1/4 over 1/4, 1. So everywhere I go on this side, if I find the slope of the secant line over here, it's 1, 1, 1, 1, 1, 1, 1. So if I take the limit from the above, what's it going to be from the secant lines on that side? 1. The limit from this side is 1. How about the limit below? Take minus 1, right? So it's 1, change in y, but the change in x is minus 1. So the slope here is minus 1. Go to a minus 1/2. 1/2 minus a half, right? So it's minus 1. Go to minus a quarter. Slope is minus 1. So if I come from the left side, the slope of the secant functions is minus 1. So notice the limit from the right side above is 1. The limit from the left side is minus 1. The limit won't exist. And you can see what happens in this picture. It's not smooth. It's not smooth. See, that's what happens. So let's go through the process and see how it works. I check the point. It's defined. It's 0. So it's 0, 0. Let's compute the secant slope function. Do it on the left. Do it on the right. And notice, again, on the left, this function is always equal to minus 1. And on the right, the slopes are always equal to 1. So we see that the secant slope function is piecewise. For x less than 0, it's minus 1. For x greater than 0, it's 1. And if you look at the limit, and here's the picture, right? This is a picture of the secant slope function. It's a function. Its slopes are always 1 for x greater than 0, and minus 1 for x less than 0. And you can see if we do the limit, it's going to be 1 and minus 1. And this is just a mathematical formulation of that. It verifies that, in fact, it's minus 1 on the left and 1 on the right. Which is what we expect. Again, intuition. It's important that you learn to think. I know we don't want you to, seems like it. But it's important that you learn to reason and think. This is the most important thing in my mind. So the limit doesn't exist. The limit from the left doesn't equal the limit from the right. So by definition, this limit does not exist. And the slope of the tangent line does not exist. And you can again see that from the picture. There's a point. So that's a function that's continuous, but not differentiable. You don't have that extra smoothness. Okay, so we're going to work a lot of these problems in the next lecture. Okay, so good luck with that.